Math and Beats, what up? Here we are again. We're gonna make a video right now on piecewise defined functions, and it is part 2 of 2 in the piecewise defined functions videos. I am using a new mic today, a headset, so I hope my voice sounds nice and smooth. Here we go. Piecewise defined functions, part 2. We're going to look at an application and also extracting the formula of one of these things from its graph. And so to begin with, just remember, piecewise defined function is a function that looks like this strange looking thing right here. This is a piecewise function. Piecewise function is some function which has different rules over different intervals in its domain. Some rule 1 over interval 1, rule 2 over interval 2, rule 3 over interval 3, etc., all the way down to some rule k, whatever it may be, on some interval I sub k. So, remember those things. We looked at it in video 1 of the piecewise functions. Right now we're going to look at an example. This example right here is one where, as you can see, we are given the graph of a piecewise defined function. We would like to find the formula for this function, which we're calling g of x here. And so we can see each piece of the function is linear. So we're going to go ahead and find each of those linear functions. But now we have to say, where are these linear functions defined? They're not defined everywhere, only on particular intervals of the input x. So on the side here, we're going to start constructing our graph. Excuse me, the rule of our graph. It's obviously called g of x. And it has 3 rules. So oftentimes if you're asked a problem like this, it's nice to first go, okay, I'm going to get the rules, but let's find the intervals for which these rules are defined. Oh yes, delicious. Okay, we have 3 different rules here given the graph. I'm going to call the first rule, that line on the left in quadrant 2, y1, the second rule, y2, and the third rule, y3. So if you look at y1, it is defined to the left of -1 for x values. So I know my first rule, y1, is going to be defined for x less than -1. The second rule, y2, is defined between -1 and 2. Notice at -1, we do not have a value. And then if I go up here to 2, there is a value there. The output is 3. So that next rule, whenever we find it, y2, will be defined on the interval of x's that is larger than -1, excuse me, and less than or equal to 2. Again, we have a value at 2 and not a value at -1. Finally, third rule, y3, we see it's defined to the right of x is 2. No value at x is 2, so this is going to be for values strictly bigger than 2. So we still need to find the rules of the function, y1, y2, and y3, and that's what we'll do now. But first, we went and found the intervals for which these rules are defined. They're all linear, these pieces, so we can use what we know about lines to find the equations of each piece. For instance, in y1, we know it's going to look like some mx plus b, m being the slope and b being the y-coordinate of the y-intercept. The slope here we can see if we go down 1 over 1, slope is -1. So m here, -1 in the first rule. And if we kept going with this graph, we would end up at 1 on the y-axis. So we know that the intercept would have been 0, 1, therefore b is 1. Hence, y1, the first rule, is -x plus a 1. All right, we're going to go ahead and replace that in our g of x here. First rule, y1, -x plus 1. That is true if x is less than -1. Second rule, we could see that if we pick the bottom left-hand point at -1, -2, even though it's not on the graph, it would be if the line kept going, and I move over to the right 1, 2, 3 units, and then up to this other point 1, 2, 3, 4, 5 units, that tells us that the slope for this second rule y2 is going to be up 5 over 3, 5/3 for the slope. And then this y-intercept here, right there, we can eyeball it. It looks like maybe it's about a third away down from the x-axis, but we can't say for sure. So we really should go ahead and find this exact location by applying the point-slope form of a line and using maybe this point up here for x1 comma y1 in our slope-intercept form. Then we're going to use y minus the output 3 is the slope 5/3 times x minus the input 2. And if you multiply out the right side there, that's 5/3 x minus 10/3. If I want to isolate the y, then I'm going to get that y is 5/3 x minus 10/3 plus a 3, adding that 3 to both sides. 3 is 9/3, -10/3 plus 9/3 is -1/3. Hence the formula 5/3 x minus 1/3. And it is down 1/3, just like we suspected, but it was nice to check. So second rule in our function, g of x is 5/3 x minus 1/3. And that is true if x is larger than -1 and less than or equal to 2. Erase some of those little things right there. And finally, y3. y3, we can see if we go down 2 units and over 1 unit, then we're on the line from that initial point. So we know that for y3, the slope is going to be down 2 over 1. That's -2. If I kept going with this line, to the left 1, upwards 2, to the left 1, upwards 2, we would be at the location 0, 3. So hence b would be 3 there, and it tells us that the equation for this line y3 is y is -2x plus 3. So g of x, its third and final rule, -2x plus 3. That's true for values of x larger than 2. And there you go. So strategy here, if you want to come up with the formula of a piecewise defined function given its graph, I always recommend first finding the different input values for which these different rules are defined, then go find the formulas for each portion of those of that graph. So we got our function, g of x. Nice function. All right. Next example, which will be the last example on this video, is an example of an application, real-world problem. It's kind of a silly one, but it gets across the point of we got to apply what we know about piecewise functions to a particular real-world situation. And here's the situation. There is some person named Johnny that works for a paper company. I wonder what paper company it is. And earns his wages by commission based on the number of boxes of paper he sells per month. And the company pays him based on this commission scale here. You see that the first $6,000 worth of paper he sells, he gets 6% on those sales. And then if he goes over $6,000, the next $12,000 after that, he's going to get 8% on each one of those amounts. And then 10% on all sales over the first $18,000. So he gets paid different rates of money on different portions of the amount of paper that he sells. Incentive, he sells more paper, he's going to get paid more. But only on certain amounts of that paper. So right here, it explains a couple of examples for different amounts of paper that Johnny here sells. For instance, if he sells $3,000 worth of paper in a month, then he's going to get $6,000 or 6% of the $3,000 because the $3,000 is less than the $6,000. So he's only getting 6% on that amount of money. That gives $180. If Johnny sells $8,000 worth of paper in a month, this is where it gets a little tricky, then he's still going to get 6% of the first $6,000 that he sells in paper. And then he's going to get 8% on the next amount up to the next 12,000. So he sold $2,000 after the first 6,000. So 8% of the next amount, 2,000, plus 6% of that first 6,000 gives a total of $520. Similarly, if Johnny has this good month selling $19,000 worth of paper, then the pay schedule says first $6,000, he gets 6% of that. Then the next 12,000, he gets 8% of that. And then finally, he gets 10% of any of the amount past the first $18,000. In this case, 10% of $1,000, since that's the only amount of money after the first 18,000. Total all that up, you got $1,420 in commission sales that month. So you can kind of already see maybe how piecewise defined function plays a role here. Let's go and find a couple of these values just to get a better understanding of the nature of this commission scale. So for instance, in part A here, how much money will Johnny make in a month if he sells $5,000 worth of paper? Well, $5,000 is less than $6,000. So that goes to pay scale number 1 up there. 6% of that money he's going to get. 6% of $5,000. If you want to turn that into mathematics, then that of course is the same as 0.06 times 5,000. And that if you press some buttons, he got $300. So just enough to pay his cable bill. How about if Johnny sells $14,000? Well, $14,000 is bigger than $6,000, right? But if we express $14,000 broken down as, okay, that's the same as $6,000 plus $8,000, and he's going to get 6% of the first 6,000. Then he gets 8% on the next 12,000, which the 8,000 falls into that category because it's less than 12,000. So you're going to get 8% of that. Therefore, 6% of 6,000 plus 8% of 8,000. Again, press some buttons. You would get that this should be $1,000. He's moving up. All right, finally, one more before we start getting functiony over here. What if he sells $21,000 worth of paper in a month? With a $21,000, breaking it down by the commission scale above, 21,000 is the same as 6,000 plus 12,000, that totals 18, plus another 3,000. The first $6,000, up to that he gets 6%. The next 12,000, 8% of that. And finally, anything after the first 18,000, he gets 10% of that. So this gives us the equation or answer of 0.06 times 6,000 plus 0.08 times 12,000, and then plus 0.1 to 10% times 3,000. Press some buttons on the calculator, you will get that he earned $1,620 that month. So this part of the promise is just supposed to help us kind of dissect how this commission scale works and get a get an idea about how maybe we could construct a function that gives us in general the amount of commission he sells, uh, amount of money he's going to get from the commission scale. So you can see in part D here, that's the first chunk that we're going to have to answer, is find an equation now that gives this commission as a function of the amount of paper sales he has. Let's call that X in a month. If he sells less than or equal to $6,000 worth of paper. So 6% up to and including the first $6,000 worth of paper, we're going to get that this function here, C of X, should be 6% of the amount he sells. So if he sells $5,000, he gets 6% of that. If he sells $1,000, then he gets 6% of that, all the way up to $6,000. And of course, we need to say that this is true if he sells nothing or up to the first $6,000. We're going to do it again, but now for the second part. Let's find a formula C that gives the function, again, which is the commission based on the amount of paper he sells in dollars, greater than 6,000, but less than or equal to 18,000. So that's that second portion there. The next 12,000. Well, if he sold more than 6,000, then he's automatically going to get 6% of that first 6,000 because he sold more than that. So the first 6,000, you always get 6% of that. But then he's going to get 8% of anything after the first 6,000, but less than or equal to 18,000. So we have to say that he gets 8% on anything after the first 6,000. For instance, if he sold $6,001 of commission in 1 month, then only that $1 after the first 6,000 will be at 8%. If he sold $10,000 worth of paper, then only the 4,000 would be given at 8%. That's why we got to subtract the first 6,000 when we plug in whatever this amount is, X, into the formula. Now, if you simplify this a little bit, that gives us 360 plus 0.08 times X minus 6,000. And that is true if, X is more, my goodness, more than 6,000, but less than or equal to 18,000. So we're kind of constructing our entire graph piece by piece here in parts D, E, and F. Finally, in part F, we want to do the same thing again as the first two, but now on any sale amount greater than 18,000. So if he sold more than $18,000 worth of paper, then he's automatically going to get 6% of the first 6,000. He's also going to automatically get 8% on the next 12,000. Too many zeros. And then he'll start getting 10% on any amount of money after the first 18,000. If you add together, again, press some buttons, the first two terms there, that is going to give us $360 plus $960, and then plus the 0.1 times X minus 18,000. And if you simplify it even further, if you wanted, you would get that this is 0.1x minus 480. So that's also distributing the 0.1 to the X minus 18,000. That's not all the way necessary, but why not? This is true for any sales larger than $18,000 in a month. So if we put all these together, we would get a single function that would give us the total amount of money that Johnny's going to get given if we sell X amount of sales of paper. So we'll piece them together, hence the application of piecewise function. First rule, it was 0.06x. That was true if 0 was less than or equal to x less than or equal to 6,000. So anything larger than or equal to 0 and less than or equal to 6,000. The next rule we had above was 360 plus 0.08 times x minus 6,000. That was for sales larger than 6,000 and up to and including 18,000. And finally, the last piece, 0.1x minus 480 if x was bigger than 18,000. Any amount of sales after the 18,000. And there we go. Now we have a single function that will give us how much money this Johnny fella is going to get in a month on commission based on how much paper he sells. A couple more parts now so you can see, like, every time we were asked a question in parts A, B, and C, we'd have to actually go through the entire process and figure out how much money he got. But now that we have a function, we could just go ahead and evaluate certain values. For instance, say I wanted to know how much money Johnny's going to get if he sells $14,000 worth of paper in a month. We know that the 14,000 falls in the range of paper between 6,000 and 18,000. So I'm going to plug in 14,000 into the formula 360 plus 0.08 times the x, 14,000 minus the 6,000. That will give me direct to the answer. And if you press a few buttons again, that gives us $1,000 he got that month. Similarly, if we wanted to figure out how much Johnny's going to get if he sells $22,000 worth of paper, well, the 22,000 falls in the category of larger than 18,000. So you plug it into that formula, 0.1 times 22,000 minus 480. And that is going to give us, again, press some buttons, that's $1,720. So there you go. The last part of this problem is just to go ahead and graph the actual function now. Notice that we don't have units here, but we assume that this function we're going to graph is the function we just found, c of x, the piecewise function. And x in units down below is tick marks 1, 2, 3, 4, and so on. This is supposed to represent the amount of dollars that he sold in paper. So probably we should label this in thousands. Thousands of dollars in sales per month. So if we sold 9,000, that just correlates to x is 9. And over there on the right, that's the commission that he gets. So if we go and look at some of our outputs up here, like here, the biggest was 1720, and that's when he sold 22,000. See it tick marks 1, 2, 3, 4, 5, 6, so on the vertical axis. So probably we want to use hundreds of dollars for units of that. So over here, we'll write hundreds of dollars in commission. And now we'll graph the function just to practice. All right, remember that function, just to refresh, it's that one right there. And so the first amount, 0.06 times x, that's just a function that starts at the origin, 0, 0. And then that is true all the way up to 6,000. So at 6,000, if you were to plug it in, 6,000 times 0.06 is 360. That is about right there or so. And then we could, let's use the fancy little thing up here. There's a line thing. Yes. Connect the dots. Whoa, it's black. Okay. That was going to be green. That's cool though. Connect the dots. All right. Just so it's nice and straight. And then the function switches rules. It switches rules to that second rule, 360 plus 0.08 times x minus 6,000. We know that at 6,000 it was 360. So the question is, what is at 18,000? Well, 18,000 18,000 times the times the 0.08 plus the 360 is approximately 960 bucks. Yeah, so I'm gonna go to 18 down here and go up to 960, but plus the 360, so that's gonna give us 1320, which is about do, 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 do. There, so hey, don't do that. Connect the dots again. Fancy little drawing thing. There we go. Connect the dots. Do it. I told you to do it. Connect it. Down here. Yes. Okay. There we go. Now we can use one more result. We know that after that, it's just 0.1x minus 480. That's that third rule. We saw when the input was 22,000, the output was 1720, so we can use that as a reference point. That very last tick mark down here, 22, the output should be 1720. So it's about right there. And then might as well just do the line thing again. Why not? I don't know why I don't ever connect right away, but there we go. And there we go. Draw a line just because we know it goes on forever. So it is piecewise, and you know the slopes of the lines looked very similar. That's because they only differ by 0.02 each time, but that is our function, c of x. And so there you have it. It's kind of a long application problem, but hopefully it helps kind of see how we can apply it to other scenarios as well. But that's it. That's it for the video. So piecewise functions is done. There is no part 3. This was part 2. Part 1 was earlier. And now we're done. We're going to do a different topic next. So piecewise the functions. See ya. What comes next, I guess you'll just have to see. All right. Hopefully that helped. Now we are done. And now it is time for some beads. Well, that's not the thing. This is the thing. Okay. Peace.